Welcome to part 3 of the Substation Design 101 lecture series. In this session, we'll briefly look at the substation lightning protection design, and then we will review the various protective relaying and control schemes. So let's start the discussion with the lightning protection design. The lightning protection system is designed per IEEE standard 998 and NFPA 780. There are basically two ways to design the lightning protection system. First is the fixed angle method shown in this slide, and the other one is the rolling sphere method coming up in the next slide. The fixed angle design method uses vertical angles to determine the number, position, and height of shielding wires or masts. The angles used are determined by the degree of lightning exposure, the importance of the substation being protected, and the physical area occupied by the substation. Both 30 and 45 degrees are widely used for angle beta. Designers using the fixed angle method may want to reduce the shielding angles as the height of the structures increases in order to maintain a low failure rate. On the other hand, as shown in this slide, use of the rolling sphere method involves rolling an imaginary sphere of radius s over the surface of a substation. The sphere rolls up and over and is supported by lightning masts, shield wires, substation fences, and other grounded metallic objects that can provide lightning shielding. A piece of equipment is said to be protected from a direct stroke if it remains below the curved surface of the sphere by virtue of the sphere being elevated by shield wires or other devices. Equipment that touches the sphere or penetrates its surface is not protected. Now let's turn our focus and attention to the protective relaying and control aspects of the substation design. We'll be covering the following concepts in protective relaying. So transmission line protection, transformer protection, distribution feeder protection, and breaker failure protection. We start with the concept of transmission line protection. Transmission line protection can be broadly divided into two categories, and they're non-pilot versus pilot protection. This slide covers the non-pilot protection, which basically means there is no end-to-end communication between the local and remote terminals. At a minimum, a transmission line is protected using three zones of phase and ground distance elements, also referred to as the ANSI device number 21. The three zones are zones 1, 2, and 3 as shown in the illustration. Typical zone 1 coverage is up to 80% of the line length. Zone 2 covers up to 120% of the line length, and zone 3 covers all the way up to the bus past the remote bus. Zone 1 has no built-in time delay. Zone 2 will typically have 20 cycle delay, and Zone 3 may have up to 60 cycle delay. These time delays need to be coordinated with the upstream and downstream devices specific to the application. In addition, there is typically a ground directional overcurrent element, also known as ANSI device number 67G, as a backup. Typically, transmission lines have auto reclosing or ANSI device 79 enabled as well. On the other hand, pilot protection of transmission lines involves end-to-end communications between local and remote terminals, which enable high-speed detection and clearing of line faults. The communication channel can be over optical fiber, radio, telephone line, or power line carrier. Also, there are several relaying schemes that are available for communication-assisted tripping. Line current differential, covered in this slide, permissive overreach transfer trip, or POTT, and directional comparison blocking, or DCB, are the most popular ones. Line current differential operates on the basis that during steady-state conditions, the current vector at the local terminal will be equal to the remote terminal. In the event that that is not true, the relays at both the local and remote terminals conclude the fault is on the protected line and trip the respective breakers. This slide shows the permissive overreach transfer trip, or POTT scheme. In this setup, an overreaching zone 2 element is typically set at 120 to 125% of the line length at both the local and remote terminals. For a fault on the protected line, both the zone 2 elements, local and remote, will pick up and send a signal to the other end. So the respective breakers are tripped when both zone 2 elements are asserted at the same time. In the case of directional comparison blocking scheme, or DCB, for the transmission line designated as the T line, there are two forward-looking zones, zone 1 and 2, as well as a reverse-looking zone, that is zone 3. This is applicable to both the local and the remote end bus, that is bus 1 and 2 in this case. So in the case of a fault F2, which is behind bus 2, the relay at bus 2 will send a block signal to the relay at bus 1, and no further action happens. In the case of a fault on the T line F1, the forward-looking zone 1 and zone 2 at both terminals will detect and send a trip signal to the respective breakers. The key here is to have minimum to no time delay for zone 2 settings. Next is transformer protection. Typically, power transformer protection involves differential and overcurrent relaying, but may include additional elements depending on the configuration of the transformer. In this example, we have a 120 MVA 34 kV to 161 kV wind farm application where the main generator step-up transformer at the collector substation is a grounded Y configuration with a delta tertiary. Let's take a closer look at how to protect this unit properly. This transformer unit is protected by an overall differential relay, or ANSI 87T, which covers the high and low side circuit breakers as well. It also has another layer of differential protection only covering the unit. In addition, both the differential relays are programmed to provide backup phase overcurrent, or ANSI 51 protection. Then there is a backup overcurrent relay providing phase and neutral protection on the 34 kV side, and another backup overcurrent relay providing protection for the 161 kV neutral and tertiary windings. A radially sourced distribution feeder is typically protected by phase and ground overcurrent elements. Depending on the characteristics of the feeder, such as its length and type, that is overhead or underground, reclosing functionality may be enabled as well. A key aspect of distribution feeder is the coordination of the substation feeder relays with downstream elements such as fuses, reclosers, and sectionalizers. A miscoordinated feeder will result in unnecessary outages. Finally, we look at the breaker failure protection. This is applicable to both transmission and distribution level breakers. The goal of any breaker failure protection is to isolate all sources of fault current contribution into the failed breaker. First step is to establish whether the breaker in question has indeed failed. This is accomplished by monitoring the trip coil of the breaker when a trip is asserted along with an overcurrent element supervised by a timer, typically set at around 10 cycles. If the timer times out, the trip is still asserted and the overcurrent element is still picked up. That means it is a breaker failure event. Subsequently, a breaker failure lockout relay is tripped, which in turn sends trip signals and transfer trip signals, if necessary, to isolate all sources. This completes part 3 of the lecture series. Please stay tuned for part 4.